So, hello everybody. Today we're going to be doing an infinite numeric series. And what we're supposed to do in this example is to check whether the infinite series as n goes from 1 to infinity of the inverse sine or arc sine of 1 over the square root of n minus the natural log or ln of 1 plus 1 over the square root of n converges or diverges. So what we're going to do here is the following. So I'm just going to rewrite this series as I'm just going to input 1 first, and then I'm going to rewrite the rest of the series. So arc sine, when we put in 1, we'll get 1 over the square root of 1, which is just 1, minus ln, by the same logic, of 2, plus the sum as n goes from 2 to infinity of arc sine of 1 over the square root of n minus the ln of 1 plus 1 over the square root of n. So the first part right here, arc sine of 1 is equal to pi over 2, and we'll just stick to this single value. We won't be putting in times 2n pi. Why? Because we really don't have to. Minus ln 2 plus, again, this series. So the series as n goes from 2 to infinity of arc sine of 1 over the square root of n minus the ln of 1 plus 1 over the square root of n. Okay, so when we're investigating whether an infinite series converges or diverges, we can use some relations which are asymptotically true. Okay, so the arc sine of 1 over the square root of n can be is asymptotically equal to 1 over the square root of n as n approaches infinity, and ln of 1 plus 1 over the square root of n is asymptotically equal to the same thing, 1 over the square root of n, as n approaches infinity. Okay, so if we were to put in these two values into here, we would just get 1 over the square root of n minus 1 over the square root of n, so that wouldn't make much sense. So instead of doing that, instead of putting this in, what I'm actually going to do is I'm going to write ln of 1 plus some function of ln of, let's say, 1 plus x. This can be rewritten as the sum as n goes from 1 to infinity of minus 1 to the power of n minus 1 over n times x to the nth power, and x here must be between minus 1 and 1. Okay? So that is the main reason why I've put out the first member of our series in front of the rest of the series. So because if we were to put in 1 right here, we would get that x is equal to 1, which would make this here representation impossible. But if we know that this series converges, the original series must also converge. So let's just go ahead and rewrite a couple of the first members. So when you plug in 1 here, you'll get minus 1 to the 0, which is 1, over 1, times x to the first power, which is just x. Then we're going to have a minus of x to the second power over 2, and so on. And that's basically plus, okay, minus 1 to the n minus 1 over n times x to the n. And this is, and we're going to be needing just the first two members. So we can actually rewrite ln of 1 plus x to be asymptotically equal to, instead of x, we'll put in, instead of x, we'll just put in 1 over the square root of n. So will be equal to 1 over the square root of n minus 1 over the square root of n squared, which is just minus 1 over 2n. Okay, now I'm going to be plugging in this value right here, and this here value right here. Okay, so we can rewrite instead of arc sine of 1 over the square root of n, instead of that we can write something else. So minus ln of 1 plus 1 over the square root of n. So we can say that this is asymptotically equal to 1 over the square root of n minus this value right here. So minus 1 over the square root of n plus 1 over 2n. Now we just have to, and these two will nicely cancel out. So we just have to see whether the series, as n goes from 2 to infinity, of 1 over 2 times n converges or diverges. Now by pulling out 1/2 in front of the series, we're just left with the series, as n goes from 2 to infinity, of 1 over n. And this series is quite well known. It's called a harmonic series, and it always diverges. So if this series diverges, which it does, then this series right here must also diverge. And if that series diverges, our starting series must diverge as well. So, in conclusion, this series diverges. So I've been using a little bit of theory, a little bit of well-known facts about infinite series. I hope you don't mind. Instead of proving it rigorously, because it's been proven many times before by a lot of other people. So I hope you enjoyed the video. If so, leave a thumbs up button and subscribe. I'll see you in the next one.